Okay, let's look at some examples from your homework. We're going to start with number 7. Number 7's a doozy. Lots of stuff going on here. So let's just look through it. It just wants us to find the derivative of this kind of pretty complex function here. The first thing I notice is I have this function multiplied by this function. What does that tell me I'm going to need to use? I'm going to need to use product rule. Product rule, I have one function here, g of x, I'll call that g of x, and then I have another function here, and I'll call that h of x. In order to use product rule, of course, I need to know the derivatives of both of these functions. Let's start with the simpler one. Let's start with h of x. H of x is just a log function. Notice it doesn't tell you what the base is. Is this base e? No, because then it would be the natural log, ln. So if it's just log without a base, remember that implies it's base 10. So this is log base 10. Well, the same logarithmic or the same derivative formula for log base a applies to log base 10. If I take the derivative log base 10 of x, I'm going to get 1 over natural log of 10 times x. The only problem is I have a function inside of the log base 10, which means I'm going to have to use the chain rule. Chain rule tells me I take the derivative of the outside function, which is, what's my outside function? Well, this is the outside function, that log base 10. That's my outside function, so I'll take that derivative first. I get 1 over the natural log of 10. Remember, that natural log piece is just based off the base. So that's not going to change with the fact that I've got a function inside of it. But then I multiply by, since this was log base 10 of a function, this is where my function goes, my inside function, 6x plus 5. Okay, so I take my derivative of my outside function, leaving the inside the same. And then I multiply by the derivative of the inside function. What's the derivative of 6x plus 5? That derivative is just 6. So that takes care of h prime, the derivative of my second piece. Let's look at the derivative of this first piece. Let's look at this whole piece. Let's look at all of g of x. What type of function is this? We obviously have an exponent here. Is this an exponential function or is this a power function? If we're looking at the big picture, this is exponential. Why? Because 2 is fixed. And where's the variable? The variable is in the exponent. So this is exponential. So when I start this, hopefully you guys recognize this is going to take the chain rule too. This is also going to require the chain rule because I have this inside function right here. But if I think about the outside function is exponential because your base is fixed and your variable is in the exponent. So as I start this, I'm going to start by using my exponential derivative formula. My exponential derivative formula tells me I just keep the function the same, but just multiply it by that natural log of a. I'm going to keep the function the exact same, but multiply by the natural log of, this is completely dependent on the base, and the base is just 2, so this is just the natural log of 2. Right? You multiply it by the natural log of whatever the base is. Doesn't matter what's in the exponent, it's whatever the base is. Okay, but that just takes care of the derivative of the outside function. Now I have to worry about the derivative of the inside function. My inside function is whatever's up in the exponent. So what's my derivative of 5x cubed minus 4? Well, that's just power rule because now this piece is a power function. Now that I'm inside, now that I'm in that exponent, now I'm working with a power function because that's what x cubed is. So my derivative there is 15x squared, and then the derivative of 4 is just 0. So I'm left with 15x squared. So those are my two smaller derivatives, my derivatives of each piece. So now I have to put this together using the product rule. So y prime or dy over dx, right? You can use either notation, is equal to, product rule is you keep the first function and multiply by the derivative of the second function. Plus, and now I do the opposite. I do the derivative of my second function, so natural log of 2 times 2 to the 5x cubed minus 4 times 15x squared multiplied by my original second function, log of 6x plus 5. So just to keep track of what we did there, Here's my g of x. Here's my h prime of x. Here's my g prime of x. Here's my h of x. That's the product rule. So I used the product rule, but within that product rule, I had to find the derivatives of each of these pieces, and both of those required chain rule. Now, I could probably clean this up, but remember, with Pearson, you can go ahead and just input it just like this, and it'll still mark you correct. Okay, let's look at another problem. This one's actually the very next problem, number 8. And this is our good applied problem. So we get to use this in an applied situation. So we have an office machine purchased for $7,500. Its salvage value depreciates according to a method called double declining balance by basically 75% each year. And so you don't have to try and come up with the equation. The equation's given to you. And what are we going to do? We're going to find the derivative, and then we're going to interpret that derivative. We have my volume formula, or not volume, sorry, value formula. And notice how we're working with an exponential function. I have a fixed base with a variable exponent. So if I want to take the derivative, I'm just going to use that exponential derivative rule right here. I just get natural log of a times a to the x. But what do I do with that constant 7,500? Using my constant multiple property, I can just keep that on the outside and just focus on this piece. And like we said, my derivative here is just natural log of whatever that base is, natural log of 0.75, and then I keep everything else the exact same, 0.75 raised to the t power. And then, of course, you can simplify this. Plug natural log of 0.75 in and multiply it by 7,500. And I get about negative 2,157 I'll round the nearest hundredth, 0.622 times 0.75 t. Now, I rounded here. The homework probably doesn't want you to round. So on the homework, just plug in this value. But the reason why I wanted to give you an actual number there is I wanted to point out the fact that this is negative. Why does that make sense? Well, this goes directly into part B. What does the derivative actually mean? And the bottom line here is a derivative is a rate of change. And what's changing? The value of the office machine. So this derivative tells you the rate at which the salvage value changes after t years. That's what the t does. Whatever number we plug in is when we're looking at the rate of change. But notice how, like I said earlier, I'm getting a negative value here. Why? The office machine is losing value. It's depreciating in value, so it should be negative. My rate of change should always be negative. Okay, those are the problems I wanted to go through. If you have any other questions, please feel free to reach out. But good luck, and I'll see you in the next video.